One kind of material that is often used in a capacitor is what's called a dielectric. And with a dielectric is a material that aligns with an electric field. So what happens is, say we've got if we put a dielectric in between the plates of a capacitor, we've got an electric field going downward. Well, if you put a dielectric material in here, the positives in the dielectric will tend to align, will tend to be pushed down, and so they'll be on the bottom, and the negatives will be attracted to the top. And so the molecules align in this way. And this creates a little mini dipole field. And because there is, and all of them are doing this, that creates a little bit of electric field going back the other direction. So filling a capacitor with a dielectric, you put a dielectric in here, it winds up decreasing the electric field, which also then decreases the potential difference. The charge is the same regardless, so that the charge in our capacitance equation doesn't change at all. But therefore, if we decrease the potential difference, we're increasing the capacitance. So that's what dielectrics are used for, is to change the properties of the capacitor. And how much a dielectric does that is measured by this. It's the Greek letter kappa, looks mostly like a K. This is called the dielectric constant. And it's just a measure of the factor by which these things change. The new electric field is the original electric field divided by the dielectric constant. The new potential difference is just the original potential difference divided by the dielectric constant. And the new capacitance is just the original capacitance times the dielectric constant. So for a parallel plate capacitor, then, the capacitance is equal to the constant times the area times epsilon naught over d. Just plugging in, this equation for capacitance. One interesting thing to note about capacitance from both of these equations is that it doesn't actually depend on anything other than the geometry of the plates. So it doesn't matter, as long as as long as you have this given charge on the capacitors, it doesn't matter what they're made of. It doesn't matter how much charge is there. All that matters for the capacitance is the geometry, the area, the distance between them. So that's kind of interesting. One way capacitors are used is in computer keyboards. You know that when you press down on a key, a letter gets typed on the screen. Well, what happens is that each key is actually has a little capacitor underneath it. When you press down on the key, it changes, the key is just sitting there, then you press down, and then the plates are closer together. So it changes the capacitance of that capacitor. And the computer circuitry detects that, and that's how letters are typed. Another application of capacitance is this really weird instrument called a theremin. I'm not even sure if that's how it's pronounced. But it's like these two antennae, and there's a little ball on top of it. And then you move your hands over the theremin, and then your hands act as the second plate. So your hand is one plate, and this is the second plate of a capacitor. And it's the same way over here, and as you move your hands, it changes the pitch and volume of what's coming out of the theremin. It's a really weird instrument. You should look up a video of someone playing the theremin, and it has a kind of a goofy sound, but it's really neat because they're creating this music without even touching the things. It's a very, very bizarre thing. One thing that happens with dielectrics is what's called dielectric breakdown. And that is, what dielectric breakdown is the voltage at which the dielectric will conduct, so that charge is able to flow between the plates of the capacitor. Essentially, this is, lightning. you get sparks between them, and so charge will be transferred between the two plates of the capacitor. There's a table for dielectric breakdown of various materials on page 711. Oh, and I forgot to mention, there's on page 710 there's a table that has dielectric constants. Excuse me. So you'll be using those pages when you do your homework. Now, I mentioned that capacitors store electrical energy. Now we know that our electric potential energy is Q E delta S, or Q times a change in voltage. Now, while charging, the potential difference of a capacitor changes. So a capacitor starts off, with just two plates, and they're connected to a battery, but initially there's no charge, and gradually the charge builds up on each plate, so that over time they gain their charge. Well, so what's in here, this voltage, it's not the voltage you get once you're done charging the capacitor. It's the average voltage is what determines the energy stored in the capacitor, and the average voltage, of course, is just the final voltage times a half, because it takes some time to charge up and establish that potential difference. So the energy stored in a capacitor is 1/2 Q times the potential difference between the plates. This is always a delta V. Since it is always a delta V, a lot of times you'll just write V and not delta V. And doing a little substitution here, we know that using the substitution that C is equal to Q over V, we can also write this as 1/2 CV squared, or as 1/2 Q squared over C, or Q squared over 2C. So those are three different ways you can write the energy stored in a capacitor. And this stored energy is used in a lot of practical applications. There's energy here. This is typically what's used in a camera flash. It's also used in a defibrillator. It's the defibrillator is the medical thing where you have the two paddles and you clear, and you shock the person to try to get their heart going again. But a defibrillator has a big capacitor that stores quite a bit of energy. Camera flash is somewhat less, but that energy is released and released as a flash of light. So those are a couple different ways that capacitors are used that stored energy is used in electronic devices. This energy here can be thought of as being stored in the electric field. We know that RU is 1/2 QV, and we know that that Q, back when I was deriving some capacitor stuff, we used this equation here, and if we look at this, then we can see, and we solve for Q, we can see that Q is epsilon naught E times epsilon naught times the electric field times the area, and the voltage across the capacitor we can rewrite as just E times delta S. Well, we're going to use the distance again as delta S, and so this then comes out to 1/2 epsilon naught E squared times the area times the distance. So this is another way of writing the energy stored in a capacitor. It's also worthwhile to define energy density, UE, which is the energy per volume. And now if you notice in the equation up here, this area times the distance between the plates, area of the plate times distance between the plates, this is the volume over which the electric field exists. So the energy per volume is just 1/2 epsilon naught E squared. And we worked out this result for a capacitor, but it turns out this is true for any electric field. So if you want to know the energy stored in any electric field per volume, you can take 1/2 times epsilon naught times the energy squared.